Okay, so this is part 2 of the video. So this is summarizing what we had from part 1. So from part 1 we showed the double integral over s of the curl is negative pi over square root of 2. So when it verifies Stokes' theorem, so in this video we will show then that the line integral of f over the boundary of s, which we're calling c, taking a positive orientation, is also this. Okay, so let me draw my surface again and we'll take a look at it. So here's my surface. So again, it was like the unit sphere, but we're looking at the part of it where z is greater than or equal to 1 over square root of 2. That's what I'm calling alpha here. So it's like the top portion of the unit sphere, where the z value is bigger than or equal to 1 over square root of 2. Okay, so our boundary then would be in here. So we have to figure out what the positive orientation is. But this is my normal vector over here. And we showed the last video that the phi goes from 0 to pi over 4. That means negative sine of phi would be negative there. So this is a normal vector. I can call it n, say. That's going to be, looks like pointing in to this sphere. So let me draw it in there. So n is my normal vector, which is this guy. So I draw it on my surface here, be pointing inwards here. So now we can figure out the positive orientation. So we'll use a little figure here to figure it out. So again, the left hand is, I marked black. So you put her head so it's in the direction of the normal vector. And imagine she's walking around the boundary here. And her left hand needs to be pointing in the direction, pointing towards the normal vectors, which it is if I go that way. So it looks like going around this way will be the positive orientation. So let me mark it in. Okay, so I've drawn in the correct positive orientation for this guy, and that's what I'm calling C now. And from part 1 of the video, we parameterized the surface itself, and we got it up here. We had these restrictions on the theta and phi. So if I want to be on the bottom portion down here, that's when the alpha, z is equal to alpha. So pretty much we're going to let z equal alpha up here. So let's do that. Okay, so z equals 1 over square root of 2, but the z from up here is equal to cosine phi. That's my z value. So you have cosine phi equals 1 over square root of 2. I want to find the angle, so we'll take cosine inverse on both sides. So phi then will equal cosine inverse of 1 over square root of 2, which is pi over 4 in radians. So then we can put pi over 4 in place of phi up here. So let's do that. And that'll be a parameterization of our guy here. But we need to make sure we have the correct orientation. Okay, so I'm calling R1 of theta then is going to be R of theta comma pi over 4. So I'm putting pi over 4 in place of phi here, here, and here. So doing that, I'll have sine pi over 4 cosine theta comma sine pi over 4 sine theta, then comma cosine of pi over 4. And the sine of pi over 4 equals cosine of pi over 4, and they both equal 1 over square root of 2. So I'm going to factor the 1 over square root of 2 out in front over here. So factoring out 1 over square root of 2, because the sine of pi over 4 equals cosine of pi over 4 equals 1 over square root of 2. So it'll become 1 over square root of 2 here, here, and here. So factoring it out in front, have it here. Okay, so this is our parameterization of C. Well, it may be the incorrect orientation, so let's figure it out. If it is the incorrect orientation, we can just put a minus sign in when we integrate, and that will rectify the situation. So let's check where we're at time 0, or when phi is 0. I'm using phi as the parameter here. You can change that to t if you want, it doesn't matter. I'm going to keep it as theta. So putting 0 in place of theta, we'll have cosine 0, sine 0, 1. Cosine 0 is 1, sine 0 is 0. So it'll be 1 over square root of 2, 1, 0, 1. That would actually put you right here. Okay, let's check now, say pi over 2 next. So putting pi over 2 in place of theta now, you'll have 1 over square root of 2 cosine pi over 2 comma sine pi over 2 comma 1. Again, I'm putting pi over 2 here and here. Cosine of pi over 2 is 0, sine of pi over 2 is 1, so it'll be 0, 1, 1, 1 over square root of 2. So it'll actually be, if you graph it there, put you there. So you can see that we'd be actually going in the wrong orientation here, because it'd be going around the other way. So to rectify that, we'll just put a minus in front of our integral that will rectify it. Okay, so let's continue. Okay, I'm going to erase a few things and summarize what we have then. Okay, so let me do that. Okay, so summarizing, we have our r up here, we have our f over here, and the theta angle goes between 0 and 2 pi. So then our line integral will equal minus, because we have to reverse the orientation, 0 to 2 pi of f of r theta dotted with r prime. So let's figure out r prime now. So it'll be derivative of this guy. The derivative of cosine would be minus sine, derivative of sine would be cosine, derivative of 1 would be 0, so let me write it here. Okay, so I've got my r prime here, so again, derivative of cosine would be minus sine, derivative of sine would be cosine, derivative of 1 would be 0. Okay, so now I have to go f composed with my r theta. So here's my f here, it's y, z, but y now is going to be sine of theta, z is going to be 1, x is going to be cosine theta, so it's going to plug into this and dot it with this then. So let me do that. Sorry, let me just point out something here. I just noticed that we had the 1 over square root of 2 out in front here. I should put that in here, because when my x then will be the cosine divided by square root of 2. So when I said it was just the cosine last time, I was incorrect. So that 1 over square root of 2, you should multiply it in so you can identify your x, y, and z. So the z would be sine theta over square root of 2, z would be 1 over square root of 2. Let me plug in here. Now let me plug in. So I get this then, so it'd be negative y is sine theta over square root of 2, minus sine times z, 1 over square root of 2, plus x cosine theta over square root of 2 times z, 1 over square root of 2, 0k, and then times, dot it with this guy here, using the I, J, K notation. So I have a square root of 2 here, and here, and here. I can actually pull that in front of the integral over here. Let's do that. Okay. And then we'll dot these also. So it'll be sine, negative sine, times negative sine here. It'll be cosine times cosine here, and 0 times 0 here. So let me do that. Okay, so I didn't factor out the square root of 2 guy yet. So it's going to be dotting these. It'll be minus sine times minus sine. So it'll be sine squared square root of 2 times square root of 2 times square root of 2. So square root of 2 cubed. And that'll be cosine times cosine, cosine squared, square root of 2 times square root of 2 times square root of 2, and 0 times 0. Let me factor out the 1 over square root of 2 cubed. And also note here, I'll note it in a second here. Actually, this minus sign should be here still. So let's factor out the 1 over square root of 2 cubed. Okay, so I factored out the 1 over square root of 2 cubed. There's a minus sign still here. Then inside I have sine squared plus cosine squared, which is 1. So let me keep going. So integrating 1 then just becomes theta. So I'm going to evaluate it 0 and 2 pi. And then square root of 2 cubed is square root of 2 times square root of 2 times square root of 2. So it's going to be 2 square root of 2. So putting 2 in place of theta then. So putting 2 pi in place of theta. So you look at this, and that reduces then to negative pi over square root of 2. And that's what we're trying to show. That's the same answer we got from part 1. So hence we verified Stokes' theorem. We've shown the line integral around the boundary equals the surface integral. So we're done.